Very good. Okay, let's get started then. So it's a great pleasure to have Alasdair Urquhart speaking for the second speaker today. He's a professor of philosophy and computer science at the University of Toronto. He's worked extensively in proof complexity, among many other topics. To this audience, he may be best known for his work on the Satan topologies. It's a great pleasure to have him here. So he's speaking on symmetric properties and Boolean complexity. So, please, Alasdair.
Thank you. Thank you, Sam. And thank you for the invitation. This is my first Zoom talk, so I apologize if there's some glitches. But thank you to Sam and Omid for help with this. The question I'm talking about today is actually kind of ancient history. It goes back to an attempt to prove P not equal to NP. It was about a bit over a decade ago. The attempt failed. The proof was incorrect. But the discussion which followed on the internet, which went on for a while, I think it had interesting consequences, and I want to talk about them. For one thing, I think one of the upshots of this was that it's a kind of barrier that the attempt that was used, which was essentially trying to prove P is not equal to NP by using the fact that the solution space of satisfiability in this case was complicated. This attempt, I think any such attempt is doomed to failure because it uses a symmetric property. So that's basically what I think we're talking about here is a kind of barrier. We know that there's barriers involving natural proofs and diagonalization, and there's various arguments showing that these are barriers. But this is, I think, a barrier that is, I think, not everyone recognizes this as being a barrier. So that's what I'm going to talk about. So the attempt that was made in 2010 was by Vinay Deolalekar, who's at HP Research Labs, I guess he's still at HP Research Labs. Anyway, it was a very clever attempt at proving P not equal to NP. It brought together a number of different areas, including statistical physics, finite model theory, and other areas in related to computer science. But ultimately, it failed. The proof didn't work. But unlike a lot of other attempts at proving P not equal to NP and P equals NP and all these kind of things, unlike those, I think there are general consequences that follow from the failure of his proof. So I think he made a genuine contribution, even though his proof didn't work. And that's what I want to talk about today. So here's how I first became aware of it. I had an email from Steve Cook in August 2010. This was to the theory group. And Steve said, this appears to be a relatively serious claim to assault P versus NP. And this paper was sent around to a lot of big names in computer science, statistical physics, and finite model theory, famous logicians on the list here. So Avi Vigderson, Lassie Lovash, Dick Karp, Neil Immerman, and so on. So you can see there's a list of very famous names here in the message. This actually got me quite excited too at the time, because for about 10 years I've been trying to prove P is not equal to NP using exactly the approach that Vinay Deolalekar was using. So this was big news for me. Thought, oh my God, he's made a success of my favorite approach to this problem. I worked, as I say, I worked for about a decade on using this approach, basically coming from statistical physics. But as it turned out, the approach didn't work, and I've now become convinced that no such approach can work. And the argument that I believe proves this is due to Ryan Williams. So basically what I'm doing here is expanding a bit on Ryan Williams' basic argument from 2010. So that's the upshot. I think this is actually a barrier to proving things about P not equal to NP or P equals NP or whatever. And so let me try and explain what's going on here. Here's the title page of the paper. I think it's still available online if you want to take a look at it. But you can explain the basics of what's going on in Dale Alasdair's paper quite shortly. So why is this not just another proof of P equals NP or P not equal to NP? You may be aware of this page that's maintained, the P versus NP page. There's over 100 papers on here, some serious, some not so serious, proving that either P equals NP or P is not equal to NP, or P equals NP is independent of set theory or whatever. It's worth looking at. It's quite interesting. And it also has a lot of amusing stuff on it, like Homer Simpson's views on P versus NP. And there's also a cartoon by Pavel Pudlak on P versus NP and things of that sort. But I think most of these papers are, they're not, I don't think anything followed from them. They're not worth following up on that case. It's just basically, they're mistakes, I think. They're just basically somebody goofed. And of course, I imagine that at least some of the audience here have proved P equals NP or P is not equal to NP or things of that sort. In my own case, I remember about 20 years ago, I remember proving P equals P space, which is even more impressive. I think you would agree. But unfortunately, of course, it was a dud. But most of these papers, I think, are not particularly interesting in terms of what followed from them. So they were sort of sterile in that sense. But Dale Alasdair's proof, on the other hand, I think was, I think it has an interesting upshot. Namely, it's not just that Dale Alasdair's proof was wrong, was incorrect, didn't work, but it seems that no such attempt as Dale Alasdair attempted, and that I was attempting around 2000 to 2010, no such attempt is possibly going to work. And that's what I want to explain. All right. So what was his approach? Here it is. I may say I think it was a very clever attempt in 2010, trying to prove P is not equal to NP. It was based on results of Achleoptis and Richie Terzaghi, a physicist. So these results were inspired by statistical physics. I'll say a little bit later on about the statistical physics underlying it. Physicists got involved in satisfiability and related things because they developed these rather strange methods involving the replica method, which is still a rather mysterious subject. So rather non-rigorous methods that they developed, but they proved all kinds of interesting things, and the results that they came up with appeared to be mostly correct, which is rather mysterious because the methods were still, they're still not understood. Later on, mathematicians and probabilists managed to make their results work, but it's still a big mystery as to why the replica method works. I think this is still an open problem. Some people like Michel Talleyrand think that the replica method is basically just a way of guessing at results, but I don't know. I'm inclined to think there's something there, but anyway. Anyway, Akliopoulos and Richie Tersengi managed to make rigorous sense of some of the predictions that were made by the physicists. And Dale Lalakar's paper was based on their rigorous version of the non-rigorous results of the physicists. All right, so what were the results here? The results from 2006 by Akliopoulos and Richie Tersengi show that if you look at an appropriate range of clause density, the space of solutions of K-SAT fragments as the unsatisfiable region is approached. So you increase the number of clauses, and then you approach the conjectured threshold, going from satisfiable to unsatisfiable, and the solution space fragments. It gets fragmented into exponentially many fragments, and the fragments get smaller and smaller. And so this is quite a striking transition as you go towards unsatisfiability. It kind of suggests that this is the reason that satisfiability, the satisfiability problem, is difficult, that there's this fragmentation in the solution space. And in fact, you can show this is true for WalkSat, and local search algorithms basically have trouble as you increase the number of clauses. But Dale Lilekar wanted to go a bit further. What he wanted to say was that this creates difficulties for any possible algorithm. Okay, and that was my own idea. I thought this was the way to go. And so I worked for about 10 years trying to make some sense of this idea. Anyway, Dale Lilekar combined these results with ideas from finite model theory due to Vardy and Immerman to argue that this fragmentation doesn't just rule out algorithms that are based on local search, but they'll rule out any polynomial time algorithm. That was his argument. Anyway, this paper of Dale Lilekar was widely circulated, and he only sent it to some big names in the complexity theory and logic community, but in fact it got very wide circulation subsequently, after it was subjected to some very difficult criticisms. Dale Lilekar complained that it had been circulated a bit too widely, and he only meant to send it to a smaller group of people. But anyway, it escaped into the wild, so to speak, and so the rest is history. Anyway, the circulation gave rise to a big discussion on the internet. Some of you may remember this from about almost 11 years ago. And there were a lot of discussion groups and mailing groups that discussed it. For example, FOM, I remember discussions on FOM with Harvey Friedman and other people. But the most interesting discussions were on Lipton's blog, Gödel's lost letter, NP equals NP. So here's the announcement from Lipton, and a proof that P is not equal to NP, question mark, August 8th. So that's just shortly after Dale Alasdair sent his paper around. He describes it as a serious proof that claims to have resolved the P equals NP question, rather similar to what Steve Cook said. Here's what he said. He's a principal research scientist at HP Labs who's done important research in various areas of networks, has also worked in complexity theory, including infinite versions of P equals NP question. He's just claimed that he has a proof that P is not equal to NP. That's right, P is not equal to NP, no infinite version, the real deal. So that's what started the discussion off on Lipton's blog. The discussion on the blog, incidentally, is still available on the internet. You can fish around. The discussions are very interesting, and but I don't have time to go into all the details of them now. So the discussion on which I'm basing my talk, there were various contributions that were made, and I think some of them are worth talking about. But the most important criticisms, I believe, were made by Ken Clarkson, Ron Fagan, and Ryan Williams, who gave a PowerPoint presentation at IBM Aberdeen. And this was reported on Lipton's blog on September 15th, 2010. Here's the first slide of their presentation. Okay, so here it is. That was a huge sensation on the internet. Computer scientist Vinay Dale Alasdair claims to have solved math's riddle of P versus NP. And the New York Times said, step 1, post elusive proof. Step 2, watch fireworks. And various other things. The Figaro, $1 million prize, has this been resolved, and so forth and so on. So this is their presentation at IBM Aberdeen. So how do they analyze the proof? Here it is. The strategy, Clarkson, Fagan, and Williams analyzed the strategy of Dale Alasdair's proof as follows. First, if K-sat were in P, then the solution spaces for all K-sat formulas would have a simple structure, quote unquote. For some K-sat formulas, the solution spaces for these formulas do not have a simple structure. That's the fragmentation that I was talking about earlier. Therefore, K-sat's not in P, and so is P is not equal to NP. Okay, so that's the proof, basically, as it's analyzed by Clarkson, Fagan, and Williams. Clarkson and Fagan make some very interesting points in their presentation, and other people made very interesting criticisms of Dale Alasdair's paper. But the most interesting objection, in my view, is the following. And I think this objection is really deadly. It goes as follows. So SAT0 is, this is a copy of Ryan Williams' slide from this presentation, by the way. SAT0 objection. SAT0 is formulas that are satisfied when you set every variable to 0, okay? Or another way of saying it, as every clause has a negated variable, okay? And this problem is definitely in P, very easy, that's clear. Just need to check the 0 assignment. However, we can show that for every K-sat formula, there's a SAT0 formula with an isomorphic solution space. All these distances between solutions are preserved. Okay, and that's important because the complicated structure that Dale Alasdair was seeing in the SAT solution space had to do with clumps of formulas and the distances between the clumps and so forth and so on. All distances between solutions are preserved. So whatever complex structure you may have in the solution space of a random K-SAT formula, there are always SAT0 formulas with analogous structure. Now, I think this is a deadly objection. And I think it's also true to say that it basically rules out any approach to the P equals NP problem, which has to do with the complexity of the solution space. And actually, Ryan Williams, in his presentation, basically said this. So what I'm doing here is I'm not being terribly original. I'm just kind of spelling out what Ryan Williams said back in 2010. The basic idea is Ryan Williams, and I think it's incredible. It's incredible what a simple objection it is, and yet it's, I think, quite far-reaching. So what I want to try and convince you of today is that this is actually a far-reaching objection to an approach to P equals NP, which in a sense corresponds to a barrier in complexity theory, similar to the ones that we face with natural proofs and oracle results and things of that sort. Okay, so that's the historical part of my talk. All of this is sort of ancient history now, but I think it's worth following up a bit in order to try to understand what's going on here. All right, so let's be a little bit more formal. What we're talking about here is the complementation group, basically the SAT0 formulas that Ryan Williams produces is just produced by complementation. So if you have a couple of formulas in KCNF, or CNF more generally, then F1 and F2 are symmetric under the complementation group if F2 results from F1 by complementing some of the variables in F1. For example, if you take that formula on the left there, then it's equivalent to formula on the right. If you complement P1, you complement P2, and you complement P23, but you leave P5 alone. Okay. And you can also, there's also an additional symmetry. You can get F from G from F if you get it by permuting variables. But it's the complementation group here that's really important, not the symmetry group of symmetrizing variables. It's actually a very ancient observation in logic that there's a kind of symmetry between negated and unnegated variables. If you look at the early literature on algebraic logic by John Venn and people like that back in the 19th century, they were quite interested in the symmetry groups of formulas, and so permuting variables and complementing variables was something they were very interested in, because if you look at the two formulas that I've written there, the equivalent formulas under the complementation group, you can see they have, in some sense, they have the same logical form, right? It's sort of arbitrary whether you write P1 or not P1. It's just symmetrical, right? It's just how you write it. So in some sense, the two formulas have the same logical form. And what's more important, and this is what underlies Ryan Williams's original observation, their logical properties are essentially the same, and that's what's crucial. All right, so let's say that a property of formulas in CNF is symmetric if the two formulas whenever two formulas F and G are equivalent under the complementation group, then they have the same property. Okay, so you can think of this as a structural property, right? It's a structural property or a property that preserves logical form. Okay, all you're doing is complementing variables. So basically, you've kept the logical form the same. Okay, you could also look at permutation of variables, but that's not a major issue here. One thing we want to do is we want to rewrite SAT a little bit. If you look at Ryan Williams's original objection in the presentation at IBM Almaden, basically he's locally complementing the variables, but you might want to different formulas when you want to rewrite a formula so that it's in SAT 0. You might, if two different formulas, you might want to, complement variables in different ways. So basically what we want is a complementation operation that works globally on SAT, not just locally. I think you could put the whole argument through if you were doing it locally, but I tried that, but it was complicated. So what we want to do is rewrite SAT in such a way that we can do this global complementation on a set of formulas. Okay, so that's the next little trick that we want to do. It's just a little trick to make the proof simpler. All right. So suppose you've got a set of CNF formulas. So X is a set of CNF formulas. Then say that this set is variable disjoint if whenever you've got F and G distinct formulas, then the sets of variables in F and the variables in G are disjoint, okay? Whenever we have such a set, then we can do a global complementation on the set, and that'll solve our problem. It's easy to rewrite a set of CNF formulas in this way without blowing it up too much. So suppose you have so there's a family of KCNF formulas satisfying the conditions that KCNF to the delta, so delta means disjoint, variable disjoint. If F's in CNF, then there's a formula F to the delta in CNF to the delta, so that this is the only place where we actually use variable permutation. So F is equivalent to F to the delta under the symmetrization group, where you're permuting variables. And the function is computable in quadratic time. None of that's very difficult. It's just a simple way of rewriting the subscripts on variables so that you get this disjointness condition, okay? All right, so this is a reformulation of KCNF, and consequently it's NP complete, okay? So what we want to do is put through the SAT 0 objection for this variable disjoint family, okay? So what's the solution space of a formula? It's just, you take suppose you have a formula in n variables in CNF, then the solution space for the formula is just this structure. It's just the Boolean hypercube, n-dimensional hypercube. You've got an edge. So this is just an edge on the hypercube when you have adjacent vertices, and then these are the points in the hypercube that make the formula true. Okay, so that's the solution space. So for sigma and tau in the hypercube, you've got E holds between sigma and tau if and only if they're adjacent vertices. And per sigma in the hypercube. This is just the satisfying assignments, that's all, okay? All right, that's the solution space. Here's an example. So here's a formula in 3 variables, P3 and not P1 or not P2. And the red vertices are the ones where it's true, and the blue vertices are the ones where it's false. Okay, so that's a small example of a solution space. Now let's say that the property of a solution space is symmetric if it's preserved under isomorphism. Okay, so if you have a formula in CNF and tau belongs to the n-dimensional hypercube, then the map, which maps sigma into sigma plus tau, is an isomorphism between the solution space S sub n of f and the solution space S sub n of f to the tau. So that's just the formula where you complement the variables in accordance with the tau in the tau here, okay? So you got a complementation on your hypercube, and the true things get mapped into the true things on the other one, okay, after you do the tau. And this is because the satisfaction is an invariant under this isomorphism, okay? And you can, if you have a symmetric property of solution spaces, then the property P, defined by just the corresponding symmetric property of the solution space, is also symmetric, okay? All right. Here's a little picture of an automorphism of hypercube. So here we've got the same solution space that I showed earlier on the left, and then here we do an automorphism on the hypercube, and the true things get mapped, true things on the right get mapped into the true things on the left, and so on, okay? So obviously the two things are isomorphic. Okay, now we come to the crucial definition. Suppose you've got a property of sets of CNF formulas, and F's a numerical function and X is a family of CNF formulas. There's a lower, here's the definition. There's a lower bound of F for X based on P if the following two properties hold. First, X satisfies the property P, okay? And the property forces the any Turing machine to take a lot of time. So for any subset of CNF, if that set has the property, then any Turing machine deciding membership in Y must take at least F of size of F steps for infinitely many F and Y, okay? So this is basically formalizing the approach that Dale Alasdair used. As we'll see later on, there's a property that he stated, which in this case stands in for P, which he claimed forced a super polynomial bound, lower bound for any algorithm for SAT. Okay, so that's his approach. All right, so here's the main result. It's basically just a formalization of what Ryan Williams said back in 2010. So a numerical function is superlinear if it basically majorizes any linear function, okay? And here's the theorem, which was implicitly stated by Ryan Williams, so I'm not making any great claim to originality here. Here's the theorem. if P is a symmetric property of sets of CNF formulas, there's no superlinear lower bound for SAT based on P, okay, using the earlier definition. So why is this true? Well, you just define a complementation so that for your variable disjoint version of SAT, every clause in F with pi applied to it contains a negative literal. Okay, that's just the SAT 0 property, right? So it's in SAT 0. But then it's obvious that there's a linear time algorithm for SAT to the delta, so no such symmetric property can exist, QED. That's it. It's an embarrassingly simple proof. I mean, there's nothing to it, right? It's just it's just the most obvious thing. I remember when I started thinking about SAT, I noticed that you could rewrite any satisfiable formula with this trick to make it obvious that the thing was satisfiable, right? It's dead obvious. There's nothing to it. So it's an embarrassing proof in the sense that it's so simple. But what Ryan Williams observed, and this was the really clever observation, is that it preserves all the crucial logical properties. It preserves the solution space, okay? So what does this mean? It means that no symmetric property of sets of CNF formulas can give you a superlinear lower bound. It's as simple as that. So what does this mean? It means not only that Dale-Lalikar's proof couldn't possibly work. I'll come to the details of Dale-Lalikar's proof later, because I have to convince you that the property he was using, which I'll call the Dale-Lalikar property, is symmetric. But anyway, I'll come back to that later. Okay. All right. So, as I said, it's an embarrassingly simple proof. There's really nothing to it. But I have to convince you that it's fairly far-reaching. It's not just a question of Dale-Lalikar's proof and the proof that I had in mind. So I was planning to amaze the world with my great contributions to P equals NP by using this sort of idea of this, complications of the solution space. So that was my plan, but Dale-Lalikar got ahead of me, and it turned out his proof was no good. But after I saw Ryan Williams's SAT 0 objection, I realized that my entire research project, which I'd been working on, like mad for 10 years, was an absolute bust. It was no good. It was hopeless. All right, so I have to convince you that symmetric properties, there's actually rather a lot of them. So let me spell out why this is so. How am I doing on time, Sam?
Let's see, you've been going for about 35 minutes.
Okay, good. Okay, so I don't need to go too slow. I can speed up a little bit. Okay, so anyway, to develop the theory of symmetric properties, we'll work within the theory, Zermelo-Fraenkel set theory with atoms. So you take the elements of the hypercube as the atoms, and then you build this set theoretical hierarchy over them. So when we think of the points in the n cube, n hypercube, as being atoms, then you can permute them. You can permute the vertices of the hypercube, and then you can extend it to the hierarchy of sets defined from 2 to the n by recursion on rank. This is a very old idea. It goes back to the 1920s, where Fraenkel proved the independence of the axiom of choice in set theory with atoms. Okay, so you can permute the atoms, and then this gives you a permutation of the entire universe. Okay, so starting from a solution space, which is similar to the solution space I defined earlier. So U is points in the hypercube, E is the adjacency relation, and T is intuitively the true formula, the true point, the points that make the formula true. Then you can define the higher order model constructed from S as this universe defined over the solution space. And then you can talk about higher order logic. Language of higher order logic. So you have a first order language with primitive symbols, membership, equality, E and T, where the variables range over this higher order universe that you defined from U. Okay, now the basic point here, which shows you that there are lots and lots of symmetric properties, is this. The basic thing is that if you look at permutations of the hypercube, then a formula of higher order logic in this set theoretical universe defined over a set of things in the hypercube is invariant under symmetries of the hypercube. Okay, so what does that tell you? It tells you that any definable property of a solution space is symmetric. It's something that Ryan Williams in his original presentation hints at, but it goes a little bit further. Basically, any definable property, any structural or definable property of a solution space is symmetric. Okay. All right, let's move on. Spaces of random formulas. This is just formulas with n variables, m clauses, and KCNF, and you can define probabilities and so on and so forth. I won't go into the details. I'm sure all of you are familiar with the SAT-UNSAT transition. There's been a lot of work on this.
So, Alasdair, can I ask a question?
Yes, sure, go ahead.
I know you wanted to go fast over that, but spaces of random formulas, is this the usual computer science model for random?
Yeah, it's basically KCNF, and you're increasing the number of formulas. This is 4SAT, going from left to right, and you can see there's a transition. This peak here represents some kind of, I'm not quite, ASAT, it's some kind of DPLL program. I'm not quite sure exactly what it is. But as you can see, there's a kind of peak around the threshold, or the conjectured threshold. The existence of a threshold number has only been verified for a high K, but anyway, that's not really important here. It does appear as if the hard formulas are here at the transition. Okay, so what's the Dale-Alekar property? I'm not going to give a precise definition of it because I can give a precise definition, but it would result in a completely unreadable slide. So it says that with high probability, a random formula in n variables and Rn clauses satisfies the following conditions. The family of true satisfying points in the solution space consists of exponentially many regions, each with small diameter, and separated from other regions by a large distance. Okay. And for sufficiently large K, in every cluster of the true points, almost all variables are frozen, which is to say they take the same value throughout the cluster. Okay. And as you approach the conjectured threshold, the clusters get smaller and smaller, and they get further apart, and it looks more and more like an error correcting code, in fact, is what's going on here. Okay.
Another question here, Alasdair.
Yes,
Is K the clause size?
K is the clause size, yes, thank you. Yes, K is the clause
Okay.
size. Right, thank you.
Yeah. Okay.
All right, so here's a picture of how things evolve. So below the threshold, we've got this big clump. And then at some point, there's a phase transition and it breaks up. The clump breaks up. And then each clump gets smaller and smaller and gets further and further apart. And things get more and more frozen. Okay, that's the picture. Okay, as I said, there's a precise definition, but I won't go into it. It just would be a completely unreadable slide. Okay, so the basic result here, and this is the result that Dale Alasdair was depending on, is that the family C and F satisfies a precisely formulated version of the property D. As I said, I'm not going to give the precise formulation. And this is the main result of a paper by Dimitris Akleopoulos and Richie Tersenghi, who's a physicist. Okay, a very nice paper, by the way, a beautiful paper. And they provided a precise version of, rigorous version of what the physicists had conjectured. All right, why is this symmetrical? Well, it's symmetric because when it's formulated rigorously, you can see that the key properties are formulated in this higher order logic I was talking about earlier. So they're all symmetric. The key properties are all symmetric. So by the earlier theorem that I stated, which is basically due to Ryan Williams, D can't be used to prove a super-lower linear band for SAT. Okay? And Dale Alasdair's proof broke down when he tried to prove so the stuff of Akleopoulos and Richie Tersenghi is all perfectly fine, but his proof broke down when he tried to prove a superlinear lower band from the property D as observed by Neil Immerman. Here's Neil. In the physicist's approach, you can also talk about I'm not going to talk about the physicist's approach very much here. If you're given a CN formula in n variables, the energy of an assignment is defined as the number of clauses not satisfied by phi, okay, an assignment. And then the energy landscape of a formula, like the solution space, is a symmetric function of F. Notice the energy landscape gives you a lot more information than the solution space, right? You know how many clauses are satisfied and unsatisfied and so on. So there's a lot of information here, but it's a symmetric function. So approaching SAT through the energy landscape is also hopeless in the sense that as long as the properties that you use to show that P is not equal to NP or whatever, as long as it's definable in this higher order logic that you've defined over your solution space or your energy landscape or whatever, can't be used to prove a superlinear lower band for SAT. This is simply because definable properties are symmetric. End of story. There is something extra you can say, though, namely, no symmetric property can rule out all polynomial time algorithms for SAT. However, for a particular proof system, you can show that there are symmetric properties of CNF formulas that can be shown to show lower bands for proof systems, and so for algorithms based on those proof systems, for example, resolution. And there's something more general you can say here. If you have an algorithm where the no instances, you look at a computation for a no instance. If this no instance can be verified by a symmetric proof system, then there are then if you can show a lower bound at all, then you can show it using a symmetric property. Okay, and lots of proof systems are symmetric. For example, Frege systems, they're symmetric. You can just flip A and not A, and you get, you know, same lower bounds. So it seems to me that the following is possible, that although there's no symmetric property that rules out all polynomial algorithms, it's conceivable that for any particular algorithm, there is a symmetric property that provides you with a lower bound. I think that's quite conceivable. But anyway, that's just my conjecture. And probably I should stop there. Thank you. Okay.
Right. Thank you very much, Alasdair. Very interesting talk. Let me clap on everybody's behalf, since they can't all do it. We have some time for questions, so we can take as much time as we need, really. So please either talk into the chat window or just speak up. And again, if someone wants to be promoted, please just raise your hand.
Can I ask a question?
Yeah.
Thank you so much, Alasdair. That was very, very interesting and bring up memories. But I wonder about the thing that you said at the end, that proof systems are symmetric. I'm having a hard time of thinking of a proof system that's not symmetric. Do you have any examples?
Oh, I didn't say all proof systems are symmetric. I just said that some of the best known proof systems, such as resolution, and resolution is obviously symmetric, and Frege systems are also symmetric. But no, I don't claim that all proof systems are symmetric. Definitely not.
So
no.
Is there an example of a proof system that's not symmetric?
Well, suppose P is not equal to NP, then we can certainly say, I think we can say that if we think of the algorithm as being a proof system, then that would not be a symmetric proof system, I think. So I don't know of an example offhand of a well-known proof system, but a lot of well-known proof systems are symmetric. That's all I can say.
Well, take a somewhat trivial example. If you just took the method of truth tables and took the solutions in lexicographic order or something like that, that would be symmetric.
Yeah. Thank you, Sam. That's a good example.
Thank you so much. Oh, yeah, that makes sense.
Thank you. Yeah, it's a good example.
Which, interestingly enough, we have well-known exponential lower bounds for, trivially.
You're right.
May I ask?
It's an automatable proof system.
Was there something else you want to say, Oliver? No. Okay, that was it. Okay. All right.
Oliver wanted to ask a question.
Oliver, did you have a question?
Okay. Hello, Alasdair. Good to see. Very good to see you. I just wanted to better understand the range of the argument, since it's yet very fuzzy to me, I must admit. Because invariance under isomorphism, that's the most basic assumption in mathematics, and thus one doesn't work without a notion which is not invariant under isomorphism is no good notion. Roughly, of course, but especially in certain circles of mathematics. And let's say we assign to any Boolean formula the shortest circuit size. And if we do the definition in the right way, then this is definitely symmetric. The names of the variables and the name and the negations don't matter. So and then we prove whatever. So every mathematical function will be finally not depending on the representation, not depending on the accidents of the representation. Actually, at least one would think so.
Right.
So and as I said, so a lower bound on that complexity function, that's what you want. And then finally, if
sure.
So therefore, of course, so it's something else. So you were discussing about the property, not this function. So I see that there's a difference, but I cannot really. Could you explain it a little bit better to me, or perhaps if you understand what my problem is?
Sorry. Say again, Oliver. What were you saying?
So
What's the
it
question?
seems to me, so your argument is, symmetry doesn't work. I, on the other hand, say, oh,
Symmetrical properties don't work. Yes,
Yeah,
that's the argument. Mhm.
Yes, but
Right.
every function, every property must be symmetric, otherwise it's not mathematical. But
Well, yeah, I understand what you're saying there, but I think that's, yeah, I mean, it's plausible to say that mathematical properties are symmetric or structural or and something like that. And if you look at, say, graph theory, then a lot of the properties that get discussed in graph theory are symmetric in the sense that they apply to unlabeled graphs, right? And what you're saying is true in general, but what Ryan Williams's argument says essentially that if you're going to prove p is not equal to np by using some property of, SAT, then it can't be a symmetric property. That's essentially what Ryan Williams's observation says. And I mean, is that a mathematical property? Well, who knows? Maybe there's a mathematical property in some broader sense. I don't know. Anyway.
yeah, so thank you. So I have to think about it. So perhaps there's a
notion. Yeah, sure.
Thank you.
Sure. I mean, it has to do with the representation of the formula. I agree. And in general, when you're thinking about logic, you don't care whether it's p or not p. As I said, you can complement the variables and you get essentially the same logical formula and has the same logical properties. The solution space is isomorphic and so forth and so on. And that's essentially why the argument works. And in the case of resolution too, let's think about resolution or other proof systems. That's a symmetric proof system. You can flip around p and not p, and you can still prove the same lower bounds. It's invariant property, the lower bounds. They're invariant under complementation.
But wasn't your argument not focused on satisfiable instances, that you can always morph any satisfiable instance in a trivially satisfiable instance? But
yes.
But you can't do anything with unsatisfiable instances.
No, you just leave them alone.
Alasdair, that's why I had the same question as, by the way, thank you for your wonderful talk. This is DJ here. But I had a similar question to Oliver's. You started by talking about symmetric properties of solution spaces.
Right.
Then at some point you made a transition to properties definable in some higher order logic, and then you had a lemma that says all properties that are definable in this logic are symmetric. And so therefore, then you made a transition to proof systems, and I quite didn't understand that bit.
Oh yes, sorry, I was rather hurrying at the end, but basically what I was trying to say in the last slide, or second to last slide, was that although there's no symmetric property that rules out all polynomial time algorithms for SAT, for particular polynomial time algorithms, such as resolution-based algorithms, for example, there are such symmetric properties which show that this particular algorithm fails in the sense that it has to be superlinear or super polynomial, rather. That was the point I was making. Excuse me there.
I think I understand what you mean by symmetric properties of solution spaces. And from that, the leap to symmetric properties of proof systems, do you mean that, I'm not quite sure what you mean. Symmetric properties of proof systems, meaning that the lower bound.
Okay, no, I was talking about symmetric proof systems. So for example, take a resolution proof and complement all the, complement the variables arbitrarily. It's still a resolution proof, okay?
Yeah.
The same is true for Frege systems. You can complement, take a Frege proof and complement the variables arbitrarily. It's still a Frege proof, makes no difference. It's symmetric in that sense. Okay, so a symmetric proof system is one where you take a proof, complement the variables arbitrarily, it's still a proof. Okay.
Mhm. Right.
And that's true for Frege systems. So if you have I mean, we don't have lower bounds for Frege-based proof systems. If we did, this would be a very powerful result. But we don't have lower bounds for Frege systems, except for very easy lower bounds. But if we did have such lower bounds, then we would have symmetric properties that prove such lower bounds. That's the point I'm making.
Is this true for all proof systems that are closed under restriction, like Frege systems?
It's just relabeling. You just relabel the variables, that's all. Restriction, yeah. I mean, restriction is, yeah, well, it's just relabeling. That's all it is. You're just rewriting the proof, complementing the variables, that's all. That's all you're doing. So that's true for Frege systems. And so if there were a lower bound for SAT for Frege-based algorithms, okay, then there would be a symmetric property that shows that. That's the point.
Okay. That makes sense. Good. Any more questions? I guess I maybe had just a short question. Since the symmetries are sort of, you're looking at the symmetries of the solution space can be gleaned by looking at the truth table of the function, obviously. And the same holds for the arguments based on, I guess, natural proofs, which take the truth table of the function. Is there any connection between natural proofs and these symmetry arguments?
Very good question. I have no idea. Maybe I should look at that. But yeah, that's a very good question. I should think about that. Thank you.
Okay, good. Any other questions?
Just a very naive question also about symmetric proof system. So if P is not equal in P, is it possible to say that no optimal proof system can be symmetric or something along those lines? Can the symmetry of a proof system be used as a way to get some kind of lower bounds?
Good question. I don't know the answer. I was just trying to argue that it's quite conceivable that, see, it's a quantifier shift. There doesn't exist a symmetric property that shows lower bounds for SAT in the way that I defined it. But on the other hand, for a given proof system, there might be such, or even a family of proof systems, there might be such a symmetric property. So it's you're shifting the quantifiers around here. I don't know the answer to your question about optimal proof systems. It's actually a very good question. So sorry, I don't know.
I think if there is an optimal proof system, then there's one that's symmetric, because you could always compose an optimal proof system with a symmetry operation on the variables first. And
that sounds plausible. Yeah,
which doesn't change satisfiability.
Yeah, I actually haven't thought about optimal proof systems.
Oh, thank you. That's very cool. Thank you.
Okay. Last call for questions. Thank you for all the discussion. I don't see anything in chat windows. All right. Thank you again, Alasdair, for a very interesting
talk.
Welcome.
You're welcome.
Very nice. Okay. And we have a fellows talk in about 20 minutes if you guys are interested in that. But for now, it's a goodbye for this week. And thank you again, Alasdair.
Thank you, Sam.
Okay. Bye-bye.
Yeah, thanks for the nice talk.
Yes.